touch the leg. So now what I'm going to do is I will do some problem of chapter number 2. So the first problem I'm going to do is calculate the potential at a point P due to a charge of 4 into 10 to the minus 7 coulomb located at 9 centimeter away. So this is something like this. This is charge having, this is equal to 4 into 10 to the power 7 coulombs, and you are going to find out potential at P, and this distance is going to be 9 centimeter. This is what I have. So you are asked to find out potential. So the given is that what is charge? Q is equal to 4 into 10 to the power minus 7 coulomb, and what is distance? R is going to be 9 centimeter, which is equal to 0.09 meter, right? And now, what is potential? The potential is given by 1 by 4 pi epsilon naught Q divided by R. And the definition of potential is, it is a work required to bring a unique positive charge from infinity to point P. This is the formula. And now, what is 1 by 4 pi epsilon naught? This is value is 9 into 10 to the power 9. Value is given. You don't need to remember this value. This is given and multiplied by. I'm not going to write units. All right. What about Q? Q is going to be 4 into 10 to the power minus 7 coulomb, and divided by the distance is going to be 0.09 meter, right? So I say 0.09 meter is 0.1. All right. So 9 into 10 to the power 4 into 10 to the power minus 7. This is 0. Like say almost 1, and this goes up. So this is going to be 4 into 10 to the power. This is equal to 0.1 is equivalent to 10 to the power minus 1. All right, minus 1 goes up. So this is going to be 10 to the power 10. This is 7, and then potential is going to be 9 fourths 36 into 10 to the power 10 to the power 3. This is 3 volt. So potential is going to be 36 into 10 to the power 3 volt. This is a potential, or I can say 3.6 into 10 to the power 4 volt. This is potentials. So what this is, and this can be written as a joule per coulomb, and this can be written as a joule per coulomb, right? This can be written as 3.6 into 10 to the power 4 joule per coulomb. Let's keep it like that. And then now the second part is, hence obtain the work in bringing a unique charge from infinity to that point. Alright, does it depends? So now you are asked to find out a work. Alright, now you are asked to find out a work. How to find out work? The second part is how to find out work, and work done. Now, work done to bring a unique charge is this much. Alright, and now work to bring a Q charge is going to be this, right? So this is going to be Q V R, right? V of R. So this. What is V of R? V of R is given by this. Alright? So this is equal to, I say V of R is going to be 3.6 into 10 to the power 4 volt. Alright. And then now what is going to be given by, this is given by Q is how much? 2 into 10 to the power minus 9. 2 into 10 to the power minus 9 multiplied by what is the potential? What is the potential? Potential is given by 3.6 into 10 to the power 4. Alright. So how much you are going to get is 2 6 12, 2 6 7.2 into 10 raised to the power minus 5 joule. This is the work. Alright. So this much work is required. Right. So alright. So this is the point. Hence obtain the work in bringing unit 2 into 10 to the minus 9 coulomb from infinity to that point is. Look at here, very simple, right? This is the work because we bring a unit charge from infinity to point P. And now this is the work because we bring 2 into 10 to the power 9 coulomb from infinity to that point. This is the point, right? So this is what I had for first problem. Now second problem is second problem, and then again it is that does the answer depend on a path along which the charge is brought? No. Why? Because this is charge path independence. So this is a conservative force. This is done in class 11. Since this is a conservative force, it is path independent, right? So this is what I have. I have two cases. This is the positive charge, which creates a positive potentials, creates an electric field. This is a negative charge, which creates a negative potentials. And I choose a point. This is a point P. This is a point Q. This is a point A. This is a point B. Right? This is I have Q like this. All right. And now look at here. Point P has a greater potentials. I write here Vp is more than. Why? Because this is a positive potential. When you talk about positive potentials, when you bring a unit charge closer, more work has to be done, right? So this is. However, in this case, it is just the opposite. Why? Because it is a negative. There is attraction, right? So Va is less than Vb. Va is less than Vb. Vb is more potential than Va is. Alright, this is what you should keep in mind. Very, very important, right? Now I'll do the problem. So figure show the electric field line of a positive and a negative charge respectively. The figure that I have shown you now. Alright, now I say give the sign of the potentials. Give the sign of potentials, right? So look at here. This is going to be a positive, right? This is going to be a positive, and this is going to be again a positive. This is again why? Because Vb is more than Va. Vp is more than Vq, right? This is now the second part is give the sign of potential energy difference of a small negative. Now here very important. Give the sign of a potential energy difference of a small negative charge between Q and R and A and B. So look at here. So if I bring a small negative charge, if I bring a small negative charge, then if I bring a small negative charge, then the potential at A, potential at P, potential energy at P is less than potential energy at Q. Why? Because this is attraction. If I bring a negative charge, there will be an attraction. Why? Because this is positive charge. However, in this case, if I have a small negative charge, there will be a repulsion, right? Then more repulsion will occur at A than B. Again, I am repeating. More repulsion occur at A than B. So therefore, potential energy at A is more than potential energy at B. This you should keep in mind. Very, very important, right? Why? Because there is less repulsions, more potentials. Alright. So therefore, there is attraction, right? This is more attractions, less attractions. So therefore, more potential energies. Or now let's see what is the What is the quotient, right? So Q is going to be more, Q is going to be less, alright? Let's say this is going to be a more than this, so this is going to be a positive, and this is going to be a more than this, so that is going to be a positive. So this is what I have. So this is going to be positive and going to be positive. Alright, positive potentials. Now next is that give the sign of work done by field in moving a small positive charge from Q to P. Small positive charge from Q to P. Look at here, again here. If I have a small positive charge, now let's say I'm sorry, maybe a little confusing, right? So I'm going to write by blue pen. If I bring up one positive charge from this to here, external work done by external force is going to be work done by, this is little confusing, work done by external force from Q to P, would be positives. If a work done by external force from Q to P to bring a positive charge, small positive charge will be a positive, then work done by field from Q to P is going to be negative. Answer is negative. Why? Because so if the work done by external force is a positive, means then the field has to be a negative. This work opposite. Force are in opposite direction, right? Now the last part is give the sign of work done by external agency in moving a small negative charge from B to A. Small negative charge from B to A. Small negative charge from B to A. Alright. So external force. Look at here. So if I have to apply a force, there is a repulsion. If I bring a negative charge Q from A to B, there will be a repulsion. So I will go against repulsions. So work is going to be positive. Work done by external agency. Work done by external agency is going to be external force is going to be positives. Work done by an external force is going to be positive. B to A, right? This is B to A. This is right. Alright, so now I've done the second problem. Now we'll do a third problem. Third problem is that determine the electrostatic potential of a system consisting of charge. So I have a system consisting of a charge, let's say 7 microfarad, let's say minus 2 microfarad, no external field, and this is going to be minus 9 centimeter. Let's say this is origin. This is going to be at plus 9 centimeters. This is along x-axis. And you are asked to find out what is the electrostatic potential, right? Yeah, what is the electrostatic potential energy of system, right? So very simple. Answer is that what is the distance between two, right? So distance is going to be distance between 7 microfarad and 2 microfarad is going to be 18 centimeter, that is equal to 1.8 meter, right? 1.8, I mean 0.12 meter. This is the. Now what about potential energy, right? So the potential energy would be equal to 1 by 4 pi epsilon naught Q divided by R. Alright, so this is equal to 9 into 10 raised to the power 9 multiplied by minus into, this is minus, this is 7 into 10 raised to the power minus 6 multiplied by minus 2 into 10 raised to the power minus 7 minus 6 divided by, what is R? R is 1.8 meter. So this is, and you are asked to do this. So when you do this, this is 18. Let's say I'll do this. 7 to 14 minus, this is a 14. 10 raised to the power minus 12. Let's say this is 18 into 10 raised to the power minus 2. Alright, and goes up. This is equal to 2, 1 by 2 into 10 raised to the power 9, 14 into 10 raised to the power 10. Why? Because this goes up, 10 minus goes up, and this is equal to 7. U is going to be minus 7, and then this is 10 raised to the power minus 1. So answer is minus 0.7 joule. This is energy. So negative, why? Because there is attraction. Why negative? There is an attraction between 7 microfarad and a minus 2 microfarad. Now how much work is required to separate the two charges away from each other, right? So look at here. The second question is, if I require this much amount of work to assemble, alright, so I say this work is required to assemble two charges. If I require 0.07 joule of work required to assemble this system of charges, if this much work is required, and how much work is required to separate? The second answer is, obviously the work required is going to be plus 0.7 joule. This much work is required. Alright. Why? Because finally this is going to be infinity is going to be 0 or minus 0.7. So minus into minus is plus. So you can do like this, or you can state like this. Why? Because work required to assemble is this much, and the work required to separate is just the opposite, right? Now next is, suppose that the same system of charge is now placed in an external field. Now placed in the external field, and this is given. External field is given. External field is given as A. This is what I am going to write now. External field is given. External field is given as A 1 by R square. And how much is A? A is equal to 9 into 10 raised to the power 5 coulomb per meter square. This is A. And then now I say you are supposed to find out energy required for this configuration, right? So we'll be having a 2 point. Alright, we'll be having a 2 point. Same charge is now placed in the external force. So I say I have a potential 1. Potential 1 is going to be electric field. Alright, electric field into distance. Alright, and then potential 2 is going to be electric field into another distance, d1, this is d2, let's say. So therefore, in a sense, what is V of R1? What is V1? I say, what is V1? V1 is going to be V by R, A by R. And what about V2? V2 is equal to A by R. A by R2, whatever, right? Alright. Now, what is the work? Total work is going to be, look at here, Q, V of R1, let's say V1 plus Q, V2 plus and Q1, Q2 divided by 4 pi epsilon naught R12. This is what I have. This is what I have, right? So you do this, alright? You can easily find out how much is R, alright? And you can easily do this and you proceed this, alright? So I've done the formula, what is V1, you find out what is V1, what is V2, and then you can easily find out, alright? R1 and R2. Okay, now next what I'm going to do is, next is this, right? Next question is, a slab of a material of a dielectric constant K has the same area as the plate of a parallel plate capacitor, but has a thickness this much, right? 3 by 4 D, where D is a separation of plate. And how is the capacitance changed when the slab is inserted between the plates? So this is something like this. I have a plate like this, and this is a capacitor, and I insert this, and this space is D, and this distance is 3 by 4 D, and this distance is D by 4. Alright, this is what I have. So this will have electric field at this point is going to be this much, and this electric field is going to be E naught. Alright, then potential, how much? Potential is going to be again this, and potential is going to be again V naught, right? This is what I have, right? Potential is going to decrease. Alright. So now what I'm going to do is, so electric field, whatever potential, right? I'll do this, right? Okay, here. So total electric field, total potential, this is a potential, right? Total potential would be equal to, without space, so this potential is given by E into D. Alright, this is D become 1/4 plus this is K and 3D by 4. This is potential. This is the total potential. Alright, so therefore potential would be equal to E, I take common out 4, and then D plus 3D divided by K, alright, and then D is again common, right? I take out this D, 1, alright, so potential would be equal to K plus 3, this is potential. Now this is the potentials, alright. Now what about capacitance? Capacitance is equal to Q by V, and charge remains unchanged, right? So this potential is going to change. So Q is going to be divided by epsilon naught. I'm sorry, this is E naught D. K plus 3 divided by K 4. Alright, now what I'm going to do is I'll put the value of Q. How much is Q? So Q is going to be sigma A. Q Q is going to be sigma A divided by epsilon naught, and then I'm sorry, Q is equal to sigma A divided by E naught G K plus 3 divided by 4. Right? This is what I have, church. I can even do like this, right? This is a church and this is electric field. I can substitute the value of electric field also. Alright? If I substitute the value of electric field, then electric field is equal to epsilon divided by sigma divided by epsilon naught, and then D divided by 4 K plus 3 divided by K. This is what I have. Alright. So sigma cancel out. Finally what I am going to get is this is equal to A epsilon naught, look at here, right? Epsilon naught A, then K 4 divided by G A plus 3, and finally I will write this is equal to 4 K epsilon naught A divided by G K plus 3. I think this is the answer. This is the answer, right? So what is this? This is going to be C naught. So therefore C is going to be C naught 4K divided by K plus 3. 4K divided by K plus 3. And I can get to this, right? If I say if medium is a vacuum, K is going to be 1. If K is 1, 1 plus 1 is 3. So this will get C is equal to C naught. This is how we verify this answer, right? So I say if in case of vacuums, K is going to be 1. K 1 plus 3 is 4. Cancel out, right? So this is for effect of dielectric if it is not fully inserted. Alright, this is what. Now I'll do a last. This is actually I've done it, so I'll just do it. I'll just give you a hint for this problem, right? Like previous problem, right? So a network over 4 capacitance, 10 microfarad capacitor is connected to 500 volt supply. As shown in figure, determine capacitance of networks. So first we are going to find out the capacitance of network. So these three are series. Look at here. I told series means negative is connected to positive, negative is connected to positive. So therefore these three are series. So what you are going to find is, so equivalent is going to be 1 by C1, 1 by C2, 1 by C3. This is how you are going to get this equivalent. And what about this? In turn, this 3 is parallel with this. Positive is connected to positive, positive is connected to negative, is connected to negative. So this is a parallel. So this equivalent, let's say this equivalent is C primes. So the total equivalent is equal to C4 plus this is that. Alright. So this is how you are going to obtain. This is first done. You do this in a room, right? And now next is charge on each capacitors. Charge on each capacitors. Look at here. Charge on all these capacitors are same, right? I write here. Charge on C1 is C1, C2 and C3 remain same. Remain same. Alright. So how much is charge? Alright, how much is charge? Potential applied is 500. Alright. C is equal to Q by V. Potential is 500. So charge is going to be, how much is C? C is equivalent primes. into potential applied. Potential is 500. This is how you are going to get it. What about charge on a C4? Let's say charge on a C4 is, let's say this is again, this is C4. Alright, this I'll write this right. C4 is equal to Q. Alright, I just say this is a Q prime divided by V, and Q prime is equal to C4V. So this is how you are going to find out. Alright. So this is the problem that I solved, and you go and try to write all the problem which I have done today. Alright. So some problem I have not given you a full answer, so you have to work out, and this problem you have to work out. Alright. And then one more problem I would like to give you is example number 2.10. You do this. Example number 2.10. Alright. You do example number 2.10. So with this, we have finished chapter number 2. So next class, I am going to do chapter number 3, that is current electricity. Thank you.